study the problems based on the Riemann criteria. In last lecture, we have proved Riemann criteria. That is, if f is bounded function defined on closed interval a comma b, then f is said to be R integrable if and only if there exists for any epsilon greater than 0, there exists a partition p epsilon such that up epsilon f minus lp epsilon f is less than epsilon. So let me write down that f is R integrable if and only if for every epsilon greater than 0 there exists a partition say p epsilon of closed interval a comma b such that u p epsilon f minus l p epsilon f is less than epsilon. This we have stated and we have proved in last lecture, and we have seen the proof is not difficult, so one can prove easily. This is very powerful result. This is called as a Riemann criteria. So this is a necessary and sufficient condition for R integrability. Right. So let me have a question now. Check the R integrability of f of x is equal to x, where x belongs to closed interval a comma b. You know, in the 12th standard, you know this is R integrable, and the integration of this is nothing but b square minus a square whole divided by 2. That is what the integration even. So what I'll be doing, I'm not interested to find out the integration. I wanted to show you how this is R integrable or why this is R integrable. So to show a function is R integrable, I have two tests. One is you find out UF, find out LF, and show that UF is equal to LF. That's a tradition, or that's a tradition that is a normal method to show a function is R integrable with the help of definition. The second part which I have is the result which we have stated, that is Riemann criteria. So this result is going to be very useful to check the R integrability. So to show a function is R integrable, what I will do, I will find out a partition in such a way that the upper sum minus lower sum should be less than epsilon with respect to that partition. If I could do that, then I will straight away say that my function is R integrable because of Riemann criteria. So well, choosing a partition is very important over here, because how you going to choose a partition is very important for Riemann criteria. Of course, it's not that simple to choose a partition. You get the ideas of partition when you solve more and more problems. Ample number of solution problem solving is needed to get the expertise to find the partitions. So now here, let me take a partition. So solution. So let let me take a partition Pn as a, which is equal to x naught comma a plus b minus a upon n comma a plus 2 times b minus a upon n comma, my third point will be a plus 3 times b minus a upon n, dot dot dot. The last point will be a plus n times b minus a upon n. But then if you see n will get cancelled and then a minus a will get cancelled. So this is basically b only. So this Pn is a well-defined partition of closed interval a comma b. So you can see this. So once I have defined a partition, then I need to define my supremum and infimum. So let capital Mi is equal to supremum of my function fx such that x belongs to xi minus 1 comma xi. In this case, what is my supremum that one need to visualize? See, you can see that this is my suppose a and this is my b. When I say f of x is equal to x, then it is a straight line passing through origin basically. Right. So this is an increasing function. So whatever rectangle I will take, suppose this is x naught, this is x naught plus this is a plus b minus a by, so basically this is x1. Now in this case, what is my x1? This is my x1. This is my x2. So this is my x1, this is my x2. Now you can see that if I form a rectangle and if I want to find out the upper sum, then supremum, then you can see that since function is increasing, the maximum value occurs at end point. So it will occur at x2. Similarly, it will occur at x1. So and so forth. So if I find out, so it will occur at x3. So and so forth. For the last rectangle, it will occur at B. So my Mi in this case will be very clear that it is f at from xi minus 1 comma xi interval, it will occur at xi only. And now what is my xi? F of xi is xi only. Similarly, if I go for the lower bound, then you can see that lower rectangle, since the function is increasing function, the lower bound will occur at xi minus 1. So small mi is equal to infimum of fx such that x belongs to xi minus 1 comma xi, and in this case it is f at xi minus 1. And what is f at xi minus 1? Because f of x is x only, so f of xi minus 1 will be xi minus 1 only again, right? So let me go for the UPF and LPF now. Now, or maybe let me write down in a more. I have seen that my Mi is f at xi, which is same as xi only. Now, how does xi looks? That is also important. Now you could see that x1 looks like a plus b minus a upon n. X2 look like a plus 2 times b minus a by n. Similarly, x3 will look like a plus 3 times b minus a by n. So similarly, xn look like a plus n times b minus a by n. So in general, xi will look like a plus I times bracket b minus a by n. So that let me write down that a plus I times b minus a by n. And similarly, my small mi is f at xi minus 1, which is xi minus 1, and which is a plus I minus 1 b minus a upon n. Right. So let me find out now UPNF minus LPNF, which is same as summation I goes from 1 to n capital Mi xi minus xi minus xi minus 1 minus summation small I goes from 1 to n Just let me put the laptop on a charging mode so that. Okay, so small mi, small mi, xi minus xi minus 1. Right. So since this subtractions is finite, or this sum is finite, we can take this is same as a common sum. We can take I goes from 1 to n, capital Mi minus small mi, and here xi minus xi minus 1. So which is same as, what is capital Mi minus small mi? That means this 2 I have to subtract. If I subtract this, a will get cancelled. B minus a by n, b minus a by n will come out common. So I minus 1 plus 1. So I will get cancelled. I will have 1 only. So b minus a by n will come here. So summation I goes from 1 to n. It will be b minus a. Yeah, let me go here. B minus a by n will come out upon n. And what is my xi minus 1? That difference is also same. So it is again b minus a upon n. And this is same as b minus a whole square divided by n square. This n and b minus a is independent of this. 1 times n times 1. Now this is same as b minus a whole square divided by n. Now this is 1 added n times 1 plus 1 plus n. So 1 added n times. So I will have b minus a whole square. This 1 plus 1 plus 1 n times. So that means n divided by n square. So one of the n will get cancelled. So b minus a whole square divided by n. So what I got is as follows: u p n f minus l p n f turn out to be b minus a whole square divided by n. My target is to show that this is less than epsilon. If I could show that this is less than epsilon, then my question is check F is R integrability. So I need to check whether. So actually I should have been given a question as prove that F is R integrable. That would have been more easy. But anyway, this is less than epsilon. Then how can you show that this is less than epsilon? The procedure is as follows. So for any epsilon greater than 0, now this would imply your b minus a whole, or maybe let me calculate this. This would imply 1 upon epsilon is also greater than 0. If epsilon is greater than 0, 1 upon epsilon is greater than 0. This would imply b minus a whole square upon epsilon is still greater than 0. Now does this true? Is this true? Yes, because b minus a whole square is greater than 0, because a and b are a point from the interval, closed interval a comma b, and b is strictly greater than a. So b minus a is strictly greater than 0. So square is also greater than 0. So because of interval properties, it is clear that b minus a whole square is greater than 0. So this ratio is greater than 0. And we know there is a nice property in a first year BSc called as the Archimedean principle. What Archimedean principle says that if you get any real number, for any real number, it is possible to find out a natural number next to it. Right. So I repeat the statement. If you want, I will write here somewhere. So what Archimedean principle says that Archimedean I will abbreviate with AP. For any x belongs to R, real number R, there exists n belongs to natural number. So let me say n naught, such that some people x is always less than n naught. So this says that for any real number, you can always find out a natural number next to it. Right. So now I am saying that this is my real number which is greater than 0 now. So by Archimedean principle, I can say that there exists a natural number, there exists n, so let me take this n belongs to natural number such that b minus a whole square upon epsilon is strictly less than n. Now in this case my x is basically this is my x. So if I am applying the Archimedean principle, so x is b minus a whole square by epsilon. So I hope this is clear. Right. So let me call this as 2 and let me call it as 1. So what I'll do, so 2 can be rewritten as this n can be taken down and epsilon can be moved to that side. So this is same as, let me add, this is same as b minus a whole square upon n is less than epsilon. Let me call it as 3. So I'll be using this 3 in 1. So from 1 and 3, from 1 and 3, we can say that u p and f minus l p and f is equal to b minus a whole square upon n, which is less than epsilon. So I have proved that u p and f minus l p and f, upper sum minus lower sum, is less than epsilon for any epsilon greater than 0. That implies that f is R integrable. So this implies f is R integrable. Right. So now take me one more problem. Let me take one more problem. So problem number 2. So f is again a function from closed interval 0, 1 to R, defined as fx is equal to 1 minus 1. 1 if x belongs to set of all rational number between 0 to 1 and set of all irrational number between 0 to 1. So what I will say otherwise, instead of this I will say otherwise. Or some people even say, instead of saying otherwise, we will say x belongs to closed interval 0, 1 minus, you have to do irrational number. So if you remove all the rational number from closed interval 0, 1, then it becomes set of all irrational number. So this graph of this function is very difficult to draw. So the question is, check f is R integrable or not. This function is going to be one of the very important example in future too. This function is also called as a Dirichlet function. Let me repeat, this function is also called as a Dirichlet function. So I need to check this function is R integrable or not. So if you want to plot this, because it is very difficult to find out the all rational between 0 to 1. Similarly, irrational. So that's a difficult task. So let's prove that solution is as follows. So let P is equal to x naught, which is 0, x1, x2, dot dot dot, xn, which is equal to 1, be any partition, be any partition of closed interval 0, comma 1. Now define capital Mi as supremum of fx such that x belongs to xi minus 1 comma xi, and similarly small mi as infimum of all fx such that x belongs to, so the same things I'm not writing now. Now what I will do, I will find out UPF. So UPF is equal to summation I goes from 1 to n capital Mi xi minus xi minus 1. Now what I want to do is as follows. Now I need to visualize you how does what will be this Mi. See, when you draw a function between, suppose this is 0 and this is 1. So this is 0, so suppose this is x1. So it is very clear that between 0 and 1 there are infinitely many rational and infinitely many irrational. In fact, there is a nice theorem called as a density theorem, which says that, you may search this theorem, density theorem, which says that between any two rational there are infinitely many rational as well as irrational, or between any two irrational numbers there are infinitely many rational number as well as irrational number. So between 0 to 1, function will definitely take value as 1 and minus 1. In fact, infinitely many times it will take value 1 as well as minus 1. So supremum value is always 1 and the infimum value is always minus 1 for any interval you take. So your Mi is always 1 now. So xi minus 1. And if you take this one outside, then this becomes a telescopic sum, which is xn minus x0. You can find out that alternate terms get cancelled. So which is uh, xn minus x0. So xn is 1 and x0 is 0. So answer is 1. Right. So UPF is a constant for any partition. So that you can easily find out what is UF. UF is equal to infimum of all UPF such that P is any partition of closed interval 0, comma 1. Of course, we started with any partition. So it is infimum of, this is 1 only. So constant infimum is 1 only. So I'll get UF is equal to 1. Now we have to find out LF. So let us write down what is LPF. So LPF is equal to summation I goes from 1 to n small mi xi minus 1. Now again, this small mi is nothing but minus 1. Again, because of density theorem, between any two rational if you take, there are infinitely many rational as well as irrational. So this will be minus 1 and this difference will give you 1 minus 0, which is minus 1. So LPF is minus 1, and if you find out supremum of that, LPF is minus 1 and my LF is supremum of all LPF such that P is any partition of closed interval a comma b. So which is equal to minus 1. So my LF I got it as minus 1. UF I got it as plus 1. So UF is not equal to LF, implies that. So this would imply UF not equal to LF implies F is not R integrable. So now we have encountered a question, a problem, or maybe we have seen a question example. Instead of saying a question, I will say we have seen an example where function is not R integrable, or a function who do not have integration. So far you have not seen any example where the function has integration or not. But now, because of this UF and LF concept, you could see that this Dirichlet function is not R integrable. Right. So let me take one more example. Question number 3. So F is from close interval 0, 2 to R, defined as f of x is equal to 0 if x is not equal to 1, and it is 1 if x is equal to 1. Right. So this function is discontinuous function, and it is discontinuous at 1. You can see that because domain is 0 to 2, and at x is equal to 1, suppose this is 1. So at x is equal to 1, this will take value 1. Rest everywhere it is 0. When x is not equal to 1, then it is 0. So let me draw it with a red line, and I should have that discontinuity. So at 1 I will say blue point. So that circle means that at 1 it is taking a jump of 1. So almost everywhere it is 0 except at 1 point, that x is equal to 1. So how will the question is, let me write down the question. Prove that f is R integrable. Right. Well, so it is almost zero function except at 1 point. So the proof is not difficult. Let me take a partition. So solution. So let p is equal to, let me take a partition as 0, comma 1 minus delta, 1 plus delta, and 2 be a partition of close interval 0, 2. Now here note that this delta is strictly greater than 0 and less than 1, because if I take delta to be greater than 1, then my partition definition will fail. So to have a non-overlapping of the subinterval, we should make sure that delta should be less than 1. Or you can say delta less than half also. Some people say it is less than half. So that should be, you can plot it and you could see that 1 minus delta, if delta is less than 1, will never go beyond 0. So it will be after 0 only. Similarly, because delta is less than 1, 1 plus delta will not go beyond 2. It will be below 2 only. Right. So this is my x0, this is my x1, this is my x2, this is my x3. Now let me go to the function. So see, here it is 1 minus delta, and here it is 1 plus delta. Now between 0 to 1 minus delta, you can see that my function is straight away 0. So my m1, capital M1 is 0, small m1 is also 0. Between 1 minus delta to 1 plus delta, my function value is 0, but at one point it is 1. So my supremum value is 1 and the infimum value is 0. And between 1 plus delta to 2, again you can see that my function is straight away 0 only. So my supremum and infimum both are 0. So let me write down that. So m1 is equal to 0 which is equal to small m1, capital M2 is equal to 1 and small m2 is 0, and capital M3 is equal to 0, which is equal to small m3. So if I want to find out UPF minus LPF, so let me calculate UPF. UPF is equal to M1 times x1 minus x0 plus M2 times x2 minus x1 plus M3 times x3 minus x2. Now what is x2, x3? This all x0, x1. So let me write down this. Now you can see that M1 is 0 and M3 is also 0. So this both will not survive. Only M2, that is 1 times and x2 minus x1. What is x2 minus x1? 1 plus delta minus 1 minus delta. So 1 1 will get cancelled. I will have 2 delta here. So it is 2 delta. So UPF is 2 delta. And for LPF, my small m1, small m2, small m3 all are 0. So my LPF is straight away 0. LPF is equal to small m1 x1 minus x0 plus small m2 x2 minus x1 plus small m3 x3 minus x2, and this everything is m1 m2 m3 itself is 0, so LPF is 0. Now my UPF minus LPF is 2 delta, so I can say that choose delta for any epsilon. I should say first, for any epsilon greater than 0, choose delta less than epsilon 2 delta, so I should say epsilon by 2. Therefore UPF, so of course delta is greater than 0, F minus LPF is equal to 2 delta, which is less than 2 times epsilon by 2, which is epsilon. So this would imply upper sum minus lower sum is less than epsilon, hence F is R integrable. F is R integrable. Right. So there is an alternate solution to this. That solution probably I will discuss in a class. So time being it is okay. Maybe in upcoming lectures we will have few more properties of R integrability along with its application. Thank you.